seismic lectures from Mike. I think the mic covered the seismic reflection, basically. So how actually we could do the seismic survey. And was there any question? Did he cover MASW as well? So can somebody talk to me? What is MASW? What's your name? Yeah. Connor. Do you remember MASW? Okay. Any volunteer? What is MASW? Is it related P wave? Shear wave? Is that like related to surface waves? Okay. And then what physical property are you saying? That the P wave velocity, S wave velocity, S wave velocity. Yeah. Okay. Yeah. Well, I want to just kind of like talk to you guys today. I think that this one is actually related to the lab on next week, but I haven't really gone through the concept of reflection coefficient and transmission coefficient. Well, I did, but I think I wasn't like spending time actually what's actually happening in let's say in 3 layers like this. So remember, do you remember NMO? NMO correction? Normal move out correction? Can somebody talk to me? What is NMO correction? Okay, so do you remember this figure? This is a source. Those are the receivers, right? And then we were trying to look at the survey doesn't look like that, but we're by sorting just this common receiver position, we could do a CMP. We can get a CMP gather, right? Common midpoint gather. CMP. Okay. So why is it common midpoint? Natalie, why is it common midpoint? Sorry. So this is the setup, and then we call this gather as a common midpoint gather. Right? And then why is it common midpoint gather? Right. Well, we're seeing basically this midpoint. Right? We got a whole bunch of different sources and receivers, but we're seeing basically like this reflection point, right? And that was the common midpoint gather. And if you actually plot how the kind of reflection event looks like in T and X plot, that looks like some sort of like this, right? And then the idea in the whole correction, we want to make it really strict, right? And the actual idea is that this was a case, but we want to change this geometry to like this, right? So suppose this was the real question, the real situation, and then we want to kind of change this geometry like this, like a normal instance. Source and receiver are at the same point. So we call this as a zero offset. Do you remember that? Okay, right. So in this case, situations are really simple, right? The source is here, so wave will go like this, and then reflection will be like that. The geometry is much easier to see the reflectors, like later. Okay. That was actually the idea of the NMO correction for seismic reflection process. Any questions? Well, this is actually my buffer time, so if you guys have questions and I really didn't get it, I spent some time. So So any more questions clear? How can we do that? Good. Well, I think rather than talking too much, I can kind of show you guys. It's actually kind of we're gonna do this in the lab, but let's open the apps. So it's called Seismology. Yeah, so that's how CMP gather look like. So if you actually measure like this, then that's the data, which is a hyperbola, right? And then we want to apply the NMO correction here. Okay. But then real data, you have like lots of noise, right? Actually, it's hard to see. And that's why we want to stack it. So we want to correct this data as a straight line. After that, we want to stack it, right? And that's actually much easier to, much better to recognize this the reflection event here. So that's actually the idea. We're going to go through it in the lab, but I'm just kind of showing you how does it feel. So how we're correcting it, we need to estimate what is the stacking velocity, right? So here, let's say I'm just changing the stacking velocity. $1,500. Let's say 2,000. Yeah, so as I change the velocity, this event is actually changing. So we're correcting the NMO. So we want to make it straight, but we need to estimate the velocity and the intercept time. That's a function of that intercept time and the velocity. It's probably. And then can you see where I'm doing it now? So I'm just trying to fit that, right? So I'm just estimating what is the velocity, stacking velocity, and the intercept time. Right. So what's actually happening? So I'm doing an NMO correction, right here, and then what I need to know the T naught, the intercept time T naught, and well, not intercept time, sorry, zero offset time T naught, and velocity, stacking velocity. And after I got this, what I'm doing, I'm stacking it. I'm just summing that over, right? This is a clean data. Suppose there are a lot of noises, right? But suppose there are lots of random noises, and then when I'm stacking it, it's going to be compensated. It'll be canceled out, and the kind of like consistent signal will be kind of amplified by stacking. So that's the kind of power of stacking and why we want to do this stacking. So like it's kind of complicated, right? Oh, okay. This wasn't the geometry. Our real geometry looks like this, right? We got source and receivers here, and then we're moving this. Okay? But somehow you need to change your geometry like this as a CNP gather, then do an NMO correction to make it as a zero offset gather, then you do a stack, right? So there's a motivation. There was a motivation why we want to do this, and basically we want to see the reflector, and then we want to get rid of all the noises. So I think that was basically, I think that's actually probably the most important concept if you're like seeing the seismic, if you're having the seismic reflection data. And then to do this process more kind of easily, I think Mike talked about the semblance plot. Have you guys remember that? No? think. Well, I think we can talk about that, I guess. Right. Have you guys seen this before? So what is actually? Okay, that's actually the frustrating time for me. Well, I thought but that's okay. But what it actually shows you is this is a function of intercept time, right? Remember what was the unknown? Intercept time and the velocity, right? Stacking velocity. That was unknown. So we want to figure that out. But I think one way you could just like try a whole bunch of that and try to fit that, which actually may not be a bad idea. But let's suppose you got multiple events, right? That's actually kind of, it's a lot of work, right? And then you have lots of CMP points, right? Sometimes there could be millions of CMP points if you are thinking about 3D seismic survey. So by clicking it and then by doing that by yourself, it can take a lot of time. So somehow you want to automate that process, right? So what it does, essentially it's a function of intercept time and velocity. So where's the pick, right? So you just need to pick this point. That's actually the optimal intercept time and velocity. So that's what it actually tells you. So what it does is it tries a whole bunch of different velocity range and the intercept time range. Well, in these days, actually nothing. Computation power is pretty good. So you can parallelize it, so there's no problem. Do it again. And then actually make a 2D plot. You can basically pick the maximum there, right? So if you got multiple reflection, you'll see that multiple of those points and basically pick that and find the stacking velocity for each reflector and then do an NML correction. So that's, I think, that was pretty much it. Okay. Now, this is the zero offset. So after an NML correction. Now, it's like a normal instance, right? Vertically, we're putting the energy in vertical direction. That's the setup. And what I'm going to do, so 1, 2. So I want to find the reflection coefficient from here to there, right? So do you remember the equation for reflection coefficient? What do we need? We need an impedance, right? So Z. J is the transmitted layer, and then I is the incident layer. So I is up, and then J is down. Okay. So that was the definition of reflection coefficient. Okay. And then you can define reflection coefficient here. Let's say this is 1, 2, 3, R 1, 2 here, and R 2, 3. Okay. So, but this R2, 3, this reflection coefficient is just between these two layers. Okay. But what is the effective reflection coefficient, which is like a ratio of amplitude of this guy and that guy? Is that same as R2, 3? Do you know what my question is?
Are you asking if it's the same going down as it is coming up?
No, there's reflection coefficient for each interface, right? But there's an effective reflection coefficient from this. So this is coming in. We're hitting this layer. It's coming out, right? But there will be an effective reflection coefficient for this full path, right? Which actually might be different from our 2, 3. Is that kind of clear what the question is now? Okay. And why that's actually important? Because that's the amplitude, what we're going to see, right? So if you actually just compute the reflection coefficient here, then I kind of suppose, oh, that might be, I'm putting 1, and let's suppose this was 1/3. The reflection energy that I'm getting is 1/3. That's not quite true, right? Because after transmitted, that energy is decreased, right? And that decreased energy is reflected here, and then coming back and transmitted and go up, right? So there are actually a lot of things happening, and if you want to kind of take account how that path, or like how much energy we are actually getting on the surface, we need to take that account. Okay, so that's actually the idea here. So if you go to processing, below seismic, there's a processing and seismic reflection. There's a section called normal instance reflection seismogram. So what it tells actually, suppose this was the case, okay, and then you can compute all the reflection coefficient for each layer. So that's the goal. But you want to know what is the effective reflection coefficient. So at the first layer, reflection coefficient of this is actually the same as that guy, just this interface between this. But at the second layer, it will be different, right? So how it looks like is like this. Yeah. So what is the effective reflection coefficient here? Is this R23 or this guy? Yeah. So yeah, so that's actually P12 multiplied by P21. So P12 stands for the transmission coefficient from layer 1 to 2. And then P21 is layer 2 to 1. So I think that actually takes account how much energy is actually decreased by transmission, right? And then you multiply by R23. And then what do you think? Is this supposed, can this be greater than 1? John, what's the reason?
How is it more?
Yeah. Perfect. Yeah. Energy needs to be preserved. And then we can't get like a greater energy than actually R23, because it's actually decreased, right? So let's suppose this was 1/3, then actual energy that you can get on the surface should be smaller than R23, right? Which is actually an important point. And after that, what you could do, so let's suppose now you can actually compute the effective reflection coefficient for each layer. So let's say this R12 star, that's the effective reflection coefficient, which is actually in this case same, right? And then R23 star, and for each layer. And then you can plot that up as a function of depth, right? So suppose this was 1/3, and then the other one might be much smaller, right? Because of, and then that's actually what, and that doesn't look like the signal, right? What we're actually measuring. So what we can do, we can convolve that seismic trace, looks like this. Feature. Have you guys heard about the convolution? What's your name? No. You heard about the convolution. Okay. So what convolution? I think that I wouldn't go into the details about what that doesn't really matter here. But the output of the convolution will look like this. So okay. So that's how the convolution works. So you got some sort of wavelet. If you convolve it, and that's the output, right? And that is actually similar to what we've seen in the app, right? Which is actually the final trace, right? Kind of stacked trace. So that was, I think, that was an important concept. And then, if let's say you could potentially have like this different sign, right? If you got a greater, like a smaller velocity below, we're gonna have a negative reflection coefficient. So you can have a whole bunch of different layers, right? So that'll generate the seismogram, which will be looked at. So we're going to walk through this in the lab, but I think it's an important concept. And also the fact that energy is actually decreased, and it's actually important to remember that. Right? So what you're actually measuring is not that big; it's pretty small. Okay. And yeah, so yeah, I'm just going to ask you a couple of questions. So suppose you did a seismic survey, and then as X T, you're seeing this type of image. What kind of wave is that? What kind of wave is that? What? Come on, guys. Direct, right? So it's a linear. It has to start from 0. How about this guy? Right. Hyperbolic reflector. And how about this guy? Refractor, right? Okay. And we've learned the Snell's law, right? Which was actually like sine theta 1, E1, sine theta 2. Okay? You guys learn it. So which one is bigger, B1 or B2? In this case. B2? So how about what happens if B1 is greater? Okay. Sounds good. Yeah. I think that's actually pretty much it for me. Is there any questions? No. On Friday, we're going to have a team TDL. So you also need to do individual TDL beforehand, read the case history. And then if you guys can sit as a group, so we're actually going to set the position now. So if you can sit as a group on Friday, it will be great to start. Okay, thank you, guys.